Good evening, viewers and subscribers. Welcome back to my channel and welcome back to another video. I want to wish all my viewers and my subscribers a happy new year, and I hope all your dreams and aspirations come through. All right. And for those of you who have recently subscribed, maximum respect, I thank you for that. Now, in my last video, I've shown you how to design a single, simple supported one-way slab. And in this week's video is going to be a follow-up video to my reinforced concrete suspended floor slab series. And today's video, I'm going to show you how to design a one-way continuous floor slab, right? So this video is going to be a long one, and the design calculation is about 12 pages. So I might break this presentation up into two parts. So this first part is going to take you through the preliminary design calculation, and part two is going to take you into the reinforcement calculation. All right. So stay tuned and watch the video until the end. All right. Thank you. So I'm going to begin the presentation by showing you how to design this continuous one-way reinforced concrete suspended slab. All right. So if you look carefully at the dimension of this slab, so we have slab 1, and slab 1 has a width of 3,800 millimeter or 12 feet 9 inches. Slab 2 has a length of 3,600 millimeter or 12 feet. And slab 3, which is 3,850 millimeter or 12 feet 9 inches. But for slab 1 and slab 3, to get the design slab, I'm going to have to subtract the thickness of the wall here, which is 6 inches, plus half the thickness of this wall here, which is 150 divided by 2, which is going to give me 75 millimeter. So this length of this first slab here is going to be 3,850 millimeter minus 150 millimeter minus 75 millimeter. So I'm going to show you where I get the final length of this slab further down into the calculation. So as usual, when we are designing for any structural member, we take a 1 meter strip, or in the event that we are using feet and inches, we take a 1 foot strip. So this calculation is going to be in metric, so we're going to take a 1 meter strip, right? So the length of the slab is going to be 26 feet 0 inches or 7,800 millimeter. All right. So here we have a section through the floor slab. So I'm going to have to give you some explanation as to this diagram. So this section is showing what we call a moment distribution diagram, okay, or a moment diagram. So if you look at the diagram here, at the beginning of the slab, we have this sag here, and it goes up, right, and then it comes up. We call this top part hug. So the bottom part we have hugging, the top part we have sagging. So it goes up, go over the support, comes down again, go up over the support, it comes down again and comes up to the last span here and then goes up. So that is what we call a moment distribution. So the reason we have this hugging and sagging is that at the first interior span, this is how the beam is going, this is how the slab is going to behave based on the uniform distributed load that is going to be applied to it, right? And at the top here, we're going to have compression, and at the bottom here, we're going to have tension. So C is for compression and T is for tension. So when it goes up above the support, because the wall here is going to be fixed to the foundation, it is going to have the tendency of pushing up into the slab, so hence it's going to create a moment. So we're going to have a reverse now. So at the top here we're going to have tension, and at the bottom here we're going to have compression, and that is why we have to put in this rebar here over the support to prevent the slab from cracking. So you see all these sign here, these squiggly line here, it represent cracking. So we're going to have cracking in the tension zone of the span, and we're going to have cracking in the upper part of the slab where we have the support, right? So the bottom portion here is what we call positive moment, and at the top is what we call negative moment. So we are going to have to design the bottom reinforcement for tension here for the first interior span, and we're going to have to design the negative moment here for the support that is going to be, for the reinforcement that is going to be over the support right here. All right, so that is why we have the bottom bar here, this top bar here, and at the corners too we're going to have to design reinforcement to withstand against the cracking. So the reason why we have cracking at the top is that when the concrete slab is exposed to high temperatures, it is going to expand. All right, and when it starts to cools down, is going to contract. So because we don't want the concrete to reduce lower or less than its original volumetric dimension, we have to put in this top bar here to prevent it from crack. And these top bar here at the top corner, at the top right here, in span 1 and in span 3, this top reinforcement here is what we call temperature and shrinkage bar. So I'm going to do some more explanation about that when we get to the design calculation. And if you have watched the first presentation, you will have seen I calculate for cracking at the top part of the upper part of the slab for our temperature and our shrinkage bar. All right, so let's jump into the design calculation now. So the first thing we need to establish about this reinforced concrete slab, if the slab is a one-way slab or the slab is a two-way slab. So to determine if this slab is a one-way slab, it is the ratio of the long side and the short side greater than 2. All right, so the long side here is 7,800 millimeter, and I'm going to choose this span of 3,600 millimeter, and we're going to divide that 7,800 by 3,600. And if it is greater than 2, it's going to be a one-way slab. So when we divide 7,800 millimeter by 3,600 millimeter, the result is 2.17, and we are getting this slab to be a one-way slab. All right. So as I said to you before, when we are designing any structural member, we do not design for the entire structural member. We take a 1 foot strip if we are doing it in imperial measurements, right, feet and inches, and if we are doing it in metric, we take a 1 meter strip. So as you can see, I have taken a 1 meter strip right throughout the length of the slab. So we're going to design just one slab. So, and since the slab basically are the same dimension, we can design for just one, or we can design all three together. All right, and I think this calculation, I have done calculation for all three slabs into one, since the dimension of since the length of the slab is different. So you see here the length of the slab is going to be something less than 3,850 when I subtract the 150 millimeter and halfway through the 150 millimeter wall. This slab is going to be 3,600, and this slab is going to be, slab 3 is going to be equal to the length of slab 1. All right. So now that we have established that we are dealing with a one-way slab, we can now look into our design parameters. All right. So we're going to use a live load of 40 pounds per square feet, or 2 kilonewtons per meter square. So our floor finishes, we're going to use 1 kilonewtons per meter square, or 20 pounds per square feet, right? And our floor finishes, you know that when you put on your slab, you're gonna put tiles on top of your slab. All right, so that 1 kilonewtons per meter square is what is accounted for the floor finishes, or your tiles. All right, and remember now you have to lay your tiles with mortar, so that is going to increase the dead load of the slab. Now our compressive stress of concrete is going to be 3,000 pounds per square inch, or 20 kilonewtons per meter square, and our yield stress of steel is going to be 60,000 pounds per square inch, or 414 newton per millimeter square. All right, so the first thing we want to do, we want to estimate the thickness of the floor slab. All right, so we're going to estimate that. So we're going to have, for the minimum height, we're going to have L over 24 for end bay, and for our interior bay, we're going to have L over 28. So let me show you where I get that from. So if we turn to table 9.5a, 9.5a, sorry, 9.5a. So table 9.5. Right, so let's see something. So we can go here, look for table 9.5, since it's giving me a little trouble. So 9.5. So this is 9.5a. So minimum thickness for a non-pre-stressed beam or one-way slab unless deflection are calculated. So since we are dealing with a continuous slab, we have one end continuous and we have both end continuous. So we're going to take the higher of these two. So since we are dealing with one end continuous, we're going to use L over 24, and for both end continuous, we're going to use L over 28. All right, so that's where the L over 24 and the L over 28 comes from. Right, so if you notice, so for the end bay is going to be that 3,850 millimeter minus 150 millimeter divided by 2. All right, so this is 3,800 millimeter, and the slab is going to come halfway through this first thickness of the wall here, and halfway through the thickness of the wall here. All right, so that's where the 150 millimeter divided by 2 comes from, and that works out to be 3,775 millimeter divided by 24, and the result is 157 millimeter, and I round that up to 163 millimeter. For our interior bay, the minimum H is going to be L over 28, which is going to be 3,600 divided by 28, and that comes out to be 128.57 millimeter, and I round that up to 129 millimeter. All right, so this 3,600 here, it comes from the middle slab here, slab number 2, 3,600. All right. So now we are going to estimate the thickness of the floor slab, right? So we are going to use the thickness, the higher thickness or the higher height of 163 millimeter, right? Which works out to be about 6.5 inches, right? So to work out our defective depth, right? So therefore the thickness of the slab, we're going to try 163 millimeter slab thickness, assuming concrete cover of 25 millimeter, assuming number 4 bars, half-inch bar, which is 12 millimeter diameter. So our effective depth is going to be equal to 163 millimeter, right, minus 25 millimeter plus 12 over 2, and that works out to be 163 millimeter. 25 plus 6 is 31, so 31 millimeter minus 163 millimeter, that works out to be 132 millimeter. So our effective depth of this 1 foot strip of concrete floor slab is going to be 132 millimeter. So let me give you a better description. So we choose a 1 meter strip or 1,000 millimeter. All right. And the depth is going to be 163 millimeter or 6.5 inches. So we estimate the rebar to be number 12 diameter bar. So and we estimate our cover for our concrete to be 25 millimeters. So from the top of the slab here down through halfway in between the rebars is going to be 132 millimeter for our effective depth, which we just calculate here. So you see we have our 25 millimeter here, which is this, and the diameter bar is going to be 12 millimeter, and since this is halfway through, we divide that by 2, and that's how it comes up to be 132 millimeter. All right. Therefore, having completed the effective depth of the slab to be 132 millimeter, we can now move to step number 2, where we compute the factored loads. All right. So for our dead load, it is going to be 0.163 meter times 24 kilonewtons per meter cube. All right. So this 0.163 meter is coming from our overall height of the slab, which is 163 millimeter. And because it's a 1,000 millimeter that make 1 meter, we move 3 decimal places to the left, and we get this to be 0.163 meters. So 24 kilonewtons, as I've said to you numerous times, that the unit weight for reinforced concrete is 150 pounds per cubic feet, or 24 kilonewtons per meter cube. All right, so that is why we times this 0.163 meter times 24 kilonewtons per meter cubes, and the result is 3.9 kilonewtons per meter square. All right. Then our total dead load now, remember we're going to use a 1 kilonewtons per meter square for our floor finishes. So therefore our total dead load is going to be 3.9 kilonewtons per meter square plus 1 kilonewton per meter square, and that works out to be 4.9 kilonewtons per meter square. So our total dead load is 4.9 kilonewtons per meter square. Now our live load, it is 2 kilonewtons per meter square. Remember, I have shown you in our design parameters, our live load is going to be 40 pounds per square feet, or 2 kilonewtons per meter square. All right. So we are going to now factor those two. So our ultimate weight is going to be 1.4 dead load plus 1.7 live load, and this we can find this in Appendix C of the ACI code. All right. So let me do a quick demonstration of that. So if you go to Appendix C here, right, Appendix C, or we could do Control Find Appendix C, right. So you see here, require strength, right? Require strength U to resist dead load D and live load L shall not be less than ultimate weight, or U, 1.4 dead plus 1.7 live. All right, so that is where that is coming from. Right, so we'll go back to our calculation now. Right, so when we times our 1.4 times 4.9 kilonewtons per meter square, and we're going to plus that to 1.7 times 2 kilonewtons per meter square, the result is going to be 6.9 kilonewtons per meter square plus 3.4 kilonewtons per meter square. When we add those two values, the result is going to be 10.3 kilonewtons per meter square. All right, but because we are using a we're designing a 1 meter strip. So therefore, load per meter strip is 1 meter times 10.3 kilonewtons per meter square, right? Because we are designing 1 meter. So it's going to be 1 meter times 10.3 kilonewtons per meter square, and that works out to be 10.3 kilonewtons meter. Okay, you see the difference? Kilonewtons per meter square as against kilonewtons per meter. So when we times meter into meter square, we're going to end up with meter. All right, so that is where we get this 10.3 kilonewtons per meter from. All right, let's move on. So we can move to step number 3. So step number 3, we are going to check the thickness of the slab for moment. All right, so we're going to use this formula here, which is BD squared over 10 to the 6 equal to the ultimate moment over 5kn. And so we have the breadth B, which is 1,000 millimeter, and D, we don't know D squared because we want to find that to see if the depth that we have chosen earlier is adequate for moment, right? 10 to the 6. Now, how we get 10 to the 6, and I think I've explained this in my previous video. We are moving from meter to millimeter, and that's 1,000. 1,000 is 10 to the 3. And we are moving from kilonewtons to newtons, and that's another 1,000. So, and that is 10 to the 3. Right? So 10 to the 3 times 10 to the 3, that's 10 to the 6. Alright, so we are moving from kilonewtons to newton because it's 1,000 newtons that make 1 kilonewton. So 10 to the 3 times 10 to the 3, 10 to the 6. So 5kn now, we do not know what 5kn is. Alright, so we're going to use this formula to calculate 5kn. So the formula is going to be phi, the open parentheses, the compressive strength of concrete times W, open bracket, 1 minus 0.59 W, close bracket, close parentheses, and where W is going to be rho over the yield stress of steel divided by the compressive stress of concrete. So we're going to take rho here to be 0.01. Alright? However, slabs are seldomly greater than slab. The rho is seldomly greater than 0.01. Right? So we're going to check the slab thickness if it is adequate. So rho is 0.01. Our FC prime is 20 newtons per millimeter square, and our Fy, the yield stress of steel, is going to be 414 newtons per millimeter square. Alright, I've shown you where these two values come from in our design parameters already. Alright, so W is going to be the rho over Fy over Fc prime, which is 0.01 times 414 newtons per millimeter square divided by 20 newtons per millimeter square, and the result is 0.207. Right? So 5kn, now we can calculate 5kn and phi for flexure or for shear. For flexure or for bending, we're going to use it as 0.9, and this is going to be the Fc prime is going to be 20 newton per millimeter square, and W, which we just calculated here, to be 0.27, open bracket, 1 minus 0.49 times 0.27, close bracket, close parentheses, and the result is 3.24. So our 5kn is 3.24. Alright? Now, we're going to work out the moment for our first interior support. Now remember, this is a continuous reinforced concrete slab, not a single simple supported reinforced concrete slab. It is continuous. It's continuous over 3 slabs. So our first interior support, let me show you where we get so our first interior support is going to be right here, this one here, right? And our second interior support is going to be here. It's going to be this one here, the support here, and these two here is going to be our NB. right? Our NBA left and our NBA right, right? NBA left, NBA right, NBA left. First interior support, second interior support, all right? So we're going to work out the moment now for our first interior support. So our first interior support, the moment is going to be WL squared over 10, where L is going to be 3,800 minus 150 millimeter minus 150 millimeter divided by 2, and the result is 3,625 millimeters or 3.6 meters. Oh, so I think I've explained that to you already. So let's go back to the first sketch. So here we have 3,800 millimeter. The thickness of the wall here is 150 millimeter, and because the slab is going to stop right at the center of the wall here, is going to be 150 millimeter divided by 2, which is going to be 75. So when we subtract all of those now, the result is going to be 3,625 millimeters or 3.6 meters. So MU, which is going to be 10.3 kilonewtons per meter. Remember, we calculate W already to be this. So WU here is going to be 10.3 kilonewtons per meter square. And since we're going to use a 1 meter strip, it's going to be 10.3 kilonewtons per meter. So we're going to calculate our first moment, right, which is 10.3 kilonewtons per meter times 3.6 meter square divided by 10, and the moment is going to be 13.35 kilonewtons meter per meter. All right. For our second interior support, we're going to use MU equal WL squared over 11. So we're going to use 3,600 minus 150, and that gives us 3,450 millimeter or 3.45 meters. So our second support here, which is this here, the distance is going to be 3,600 minus 75 minus 75. So that's minus 150 millimeter, right? And that's how we get our length to be 3.45 meters. So the moment is going to be 10.3 kilonewtons per meter times 3.45 meter square divided by 11, and the moment works out now to be 11.14 kilonewton meter per meter, right? So therefore we're going to use the higher moment of 13.35 kilonewtons per meter, right? We're going to use the higher moment. So we get our first interior support, the moment is 13.35 kilonewtons per meter, and our second interior moment is going to work out to be 11.14 kilonewtons per meter, and we choose a higher of 13.35 kilonewtons per meter. All right. So now we can work out our D, our depth, right? So we have MU, which is 13.35 kilonewtons per meter times 10 to the 6, and I've shown you where 10 to the 6 comes from, over 5 kN, which is 3.24. Remember, we calculate 5 kN up here to be 3.24, right? So when we work that down, now we're going to make D the subject, so we're going to find the root. So when we get BD squared, when we times the 13.35 times 10 to the 6 divided by 3.24, the result is 4,120,370.37 millimeter cube. All right. So we are designing a 1 meter strip, so we know B is going to be 1,000 millimeter or 1 meter, right? So we're going to use 1,000 millimeters. So it's going to be 4,120,370.37 divided by 1,000, and we're going to find the root of that. Since we are using D square, right? We want this to be the D only, so we want to get rid of the square. So we find the square root of the result of this, which works out to be 64.19 millimeter. All right. So therefore, D is 64.19 millimeter, and to keep rho equals 0.01, since D, which we calculate earlier to be 132 millimeter, exceeds the minimum of 62.19 millimeter, the slab will be okay for flexure or bending. All right, so we do not have to do a deflection calculation because the thickness of the slab is of such that our deflection will be safe. All right, now I'm going to move to step 4 now. So to check whether the thickness of the slab is adequate for shear. And as I said to you before, we do not usually have shear reinforcement in reinforced concrete slab. For beam, it is different. Alright, but we usually don't have shear reinforcement for concrete slab, but nonetheless we are going to do our shear calculation to verify if the slab indeed doesn't want any, it's not necessary for any shear reinforcement. Alright, so we're going to use 5 VU is greater than 5 VC, and we're going to, and we can find this into ACI section 11.5.5 1A and 11.5.61. Alright, you can look that up. So since it is difficult to place shear reinforcement in a slab, the upper limit VU will be taken as 5 VC, right? And since all the spans are unequal, VU is going to be 1.15 times W times the nominal length divided by 2, right? So for our first interior, the span length is 3,625 millimeter or 3.6 meter. I've shown you where that comes from already. So we're going to work out our ultimate shear here to be 1.15 times 10 to 10.3 kilonewtons per meter times the length, which is 3.625 divided by 2, and then we are getting a shear of 21.46 kilonewton meter of width. Right? For typical interior support, our LN is going to be 3,450 millimeter or 3.45 meter. So our VU is going to be 10.3 kilonewton meter times 3.45 meter divided by 2, and the result is going to be 17.76 kilonewton meter of width. Alright, so our 5 BC, right, and this is coming from the code again, is going to be equal to 0.85 the root of this compressive strength of concrete times the breadth times the depth divided by 6. Alright, now for shear reinforcement, we usually take 5 of 0.85, right? And for flexure, we use 0.9, all right? So it's going to be 0.85, right, times the root of 20 Newton millimeter square, which is the compressive stress of concrete, times 1,000 millimeter, 1 meter strip, times the effective depth of 132 millimeter divided by 6, and we get a shear of 83,628.94 newtons or 83.62 kilonewtons. All right. Now, since 5 VC is greater than VU, where 5 VC is 83.62 kilonewtons, and our ultimate shear is equal to 21.46 kilonewtons, and since 5 VC is greater than VU, slab is adequate for shear. Therefore, we can use our dimension of our nominal height to be 163 millimeter, and our effective depth to be 132 millimeter, and our ultimate weight on the slab, which is the live load plus the dead load, is going to be 10.3 kilonewtons per meter square. All right. Now we're going to move to the design of our reinforcement, and I'm going to stop the video here and continue this video next week, because there still is a lot of explanation to do where the design of the reinforcement is concerned. All right, so next video I'm going to pick up where we left off here, but let me show you what we are striving to get in our design reinforcement. So after we have been through the calculation, so this is the reinforcement, the slab reinforcement in plan, and this is the slab reinforcement in section, right? So these are what we are striving to get to calculate the spacing of the rebar for our positive moment and the spacing of our rebar for our negative moment and our temperature and shrinkage bar. All right, so next week, if you want to know how I arrive at those two details, you have to ensure that you watch the video next week to see how I do those calculations. All right, so make sure to tune in for the next video to see where I come up with the design reinforcement for the continuous one-way slab. All right, watch the video until the end, like, share, and subscribe, and ask me questions in the comment section. Enough respect. Thank you.